So far, we've looked at electrostatic forces from an action at a distance perspective, but now we're going to change our perspective. So James Maxwell addressed this by first saying that physicists were really tired of this whole action at a distance thing, and we're looking for new ways to look at such phenomena. So Maxwell developed his theory of electromagnetic fields, described by his Maxwell's equations. So in Maxwell's world, the field is its own physical entity, so pretend this is the field, and it carries some sort of momenta and energy across space. So it's almost like something radiates outwards from a point source. And the whole idea of action at a distance is now all due to the apparent effect of local interactions of charge with their surrounding field. So if you have a charge here and it generates a field, then over here another test charge is going to experience the effects of that field at that point. So before we can have a meaningful discussion about electric fields, we kind of have to take a step back and look at vector calculus and vector fields. Once we understand how to read different field graphs, and also calculate electric fields, then we'll be able to have better discussions about electric fields and many more things. So instead of focusing on action at a distance, where one object has an effect on another, we now want to focus on a new point of view. And that point of view is going to be from fields. So the first question I want to ask is, what is a vector field? And to answer that, a vector field basically comes from vector calculus. So in vector calculus in physics, we assign a vector to each point in a subset of space. So if I draw my x and y axes as an example, I have my x and y, and let's just say I have a few tick marks on each axis. So that means I can look at several points, which I'll draw out here very roughly. So I have some sort of a grid system, and let's say I have some sort of point source here. If I want to take a look at the field lines or the field vectors, I would look at each individual location on this grid. For example, I'll take a look at this one at 1, 1, and maybe there's going to be a field strength in this direction at this point. If I take a look at the coordinate system 0, 1, maybe there's a field vector pointing upwards towards the y-axis of the same magnitude. And so I can keep doing something like this, these points. And as I radiate out, I can have different values. So this is just an example. But the idea is that each of these vectors here, each vector, or each field vector, is an arrow with the following properties. It has magnitude, and it also has length. Whoops. It has magnitude and length, as well as direction. So that's what makes it a vector. It's also very useful in observing different physical phenomena. So for example, just by looking at this example grid of a bunch of vectors and arrows, you can kind of feel that you can mimic the motion of fluid throughout space. So in fluid dynamics, a lot of field vectors are used to try and represent moving fluid throughout space. An example of moving fluid throughout space is also wind going through the air. So there are weather maps, and if you take a look at weather maps, there are arrows that represent the strength and direction of wind. So if you take a look at one of those vectors, the longer the vector or the arrow, the stronger the wind at that point, and it also will tell you the direction that the wind is pointing in. And of course, it's very useful for magnetic, electric, or gravitational force observations, especially as it changes from one point to another. So for us, we will be using vector fields to describe electric fields.